right, everyone, good morning and welcome to Probabilistic Machine Learning. Can you hear me? Is this loud enough? Is it too loud? It's probably a little bit too loud, right? How is this? No? No, it's not too loud? Okay, good. So people at the back can hear. Welcome, everyone. I have a sense that some of you are just joining us from across the street from statistical machine learning. How many of you were in the statistical machine learning lecture? Good. So I actually only found out this morning that it's in the other building. I thought it was in here. But, well, I hope it's close enough that you can walk over, and we're starting 1:15, so there should be enough time. When they asked me what kind of lecture hall I would need for this lecture, I actually didn't say I needed this big room. I said I'd need room for like 100 people. And then they gave me this massive room anyway, maybe because I have a history of causing sit-ins and occupations in the Kupferbau when I give this lecture. But let's see if that happens this year or not. It's certainly enough space for you. And then maybe towards later in the year, once the new building is finished up on the hill, maybe we can move all of these lectures up there, including the statistical machine learning. So maybe let's see the converse as well. How many of you did not attend the statistical machine learning this morning? That's maybe roughly half. OK, that's good. So for those of you who were in the other lecture, you may be wondering why you have these two lectures side by side, one after another. I'll say more about this later. But because it's in the other building, I couldn't actually come over and sit in and see what Matthias Hein is doing. But I'm assuming that he went through a whole list of different things that he's going to cover over the course of this year. This course, in a way, if you like, is just going to be about one thing and one thing only for the entire term, and that's Bayes' theorem. So hands up, who has seen Bayes' theorem before? Very good. Who has not seen Bayes' theorem before? That's very good. I was hoping that there would be one or two hands just in the very back. So for those of you who just raised your hands, you've seen this expression before and you're already bored and you think like, why should I be here for the entire term if this is all we're going to do? So you've heard about this equation that relates different quantities to each other. So let's spend the next few minutes just thinking about what this theorem actually says. Maybe a first view is that you've probably also seen is this sort of philosophical interpretation. Right? Maybe you've encountered Bayes' theorem first in a statistics class, in your third term or so, in a math class, where you've learned about these philosophical interpretations that this equation relates prior knowledge about some latent quantity we may be interested in to posterior knowledge about this quantity given data. Why? Here is some data. How does it relate this? Well, through a function called the likelihood, which is the conditional probability for the data given the hypothesis or given this latent quantity, divided by what's called the evidence. Another way of thinking about this mathematically is that it relates a conditional probability to a joint generative model by dividing by a marginal probability. Or maybe it applies two different rules of probability theory. I guess that you've seen all of these different interpretations and that you're feeling right at home now. Maybe you've also noticed that this equation is actually more sort of closer to the perspective of computer science, an operation that operates on arrays. It's a statement about relationships between vectors that you can construct by operating on an array. If you have a discrete set of possible outcomes that you can write in a joint distribution, that's an array with two dimensions over x and y, then you can compute these marginal quantities, these p of x's and p of y's, by summing this array along different dimensions. And now here's your first question to you. How do I get to likelihood and posterior in this view? What do I need to do with these arrays? Suddenly silence. Maybe it's not so obvious after all. Where's the posterior distribution in these expressions? The 1 over x. given y? Yes? We normalize each column. What do you mean by normalize? You make them sum to 1. So what's the actual operation I need to do with the things that are on the slide? It's actually here, right? I mean, you can read it off. It's a broadcast divide, right? So I take this big array and I divide it by P of y. Then I get the posterior. That's it. And likely, or similarly, if I divide by this, what do I get in a broadcast fashion? The likelihood. Thanks a lot. So probability theory is array programming. That's what it is. And that's why in machine learning these days, array-centric programming paradigms are prevalent. And so over the course of this semester, you're going to get to see me use a lot of code in the domain-specific language JAX, which is like a souped-up version of NumPy that allows very efficient operations in Python. It's basically a tunnel out of Python to do efficient for loops over arrays. And in JAX, you could use a piece of code like this to construct all these objects, the prior, the evidence, the likelihood, and the posterior by doing these kind of operations. And at first, if you haven't seen JAX before, if you haven't used NumPy much, then these operations look maybe a bit alien to you because they use this broadcast notation a lot, but you will get used to these expressions. They're actually very elegant, and they allow us to do quite powerful operations in single lines of code. I should also say that JAX is still sort of a moving target. So every time I teach this course, I need to update some of the code. And you may notice sometimes that when you look at the code I'm using, that sometimes you may see things that look a lot like 2025, and sometimes they look a lot like 2018, because maybe they are. This is maybe a case of this. So the reason I'm showing you this is twofold. One, to highlight the fact that arrays are going to be very important in this course, and that they are very fundamental to machine learning these days, because machine learning is probabilistic. Why? Because probabilistic statements are statements about entire arrays rather than individual elements in arrays. That's maybe one way to characterize the difference between probabilistic and statistical machine learning. You're going to hear more and more of these. The other reason to show you this is to highlight that there is only one object we need to define a probabilistic model, and that's this joint distribution. If I hand in this joint distribution to this function, it provides everything I need. It provides a prior, a likelihood, a posterior, an evidence. Everything is already constructed. So if you can write down a joint probabilistic model, a joint distribution over all the variables that you care about, you're done, at least on paper. On a computer, we'll have to spend a little bit more time to make things efficient. Another way to think about probability theory and why it is relevant, why you should care about something called probability theory, is that it is an extremely powerful notion that generalizes the formalism of classic, let's say, Aristotelian logic or classic propositional logic. You all know this sort of old adage that in classic logic, there is no way to disprove a hypothesis if you only have evidence supporting the hypothesis. Or to put it in this sort of famous saying, maybe by Karl Popper or maybe by Aristotle, absence of evidence is not evidence of absence. If I have an hypothesis that every raven in the world is black, and I only ever observe black ravens, then I can't actually prove that the hypothesis is true. Why? Well, maybe one easy way to see this is that under the rule from H follows O. So here I have a hypothesis and an observation, right? The observation is I've seen a bunch of black ravens. The hypothesis is every raven is black. Clearly, the hypothesis would imply the observation, right? So this logical rule is true. Then you can look up in a truth table what this true observation tells you about the hypothesis, it tells you absolutely nothing. Because if the hypothesis were false, it would still be possible to observe ravens and just be unlucky, basically, right? And never get to see one that isn't black. And so in classic logic, and this has actually, I mean, this has been a problem for philosophers of science or was a problem for philosophers of science for centuries, ever since the ancient Greeks. There was no way to sort of formalize this intuitively true notion that if I go through life and I keep observing only ever black ravens, that I should probably become more confident in the hypothesis that ravens tend to be black, right? Or that all ravens are actually black. So probability theory allows us to make these kind of inferences, and it does this by using two tricks. The first one is, in this picture over here, that we introduce this black square around the space of observations. And what this sort of symbolizes is that we assume that there is a finite amount of possible things that could happen. That's going to become relevant in a second. It's maybe a bit unclear yet, but it's going to be very relevant, actually. It's one of the key assumptions. And the other assumption will be something even more complicated that I will gloss over in the next few minutes, and then we'll get back to it in a few minutes. Maybe first, we can confirm that the statements that you already know, Bayes' theorem, probability theory, sort of fits within this framework of classical logic, or actually classical logic is a corner case of it. In the special case where we have deterministic relationships, so where a hypothesis strictly implies an observation, that means that the probability of H and O is equal to the probability of H. So that means there is no such sort of external part, right? So this overlap is complete. H is completely within O. You can sort of read off that the posterior probability for the observation, given the hypothesis, or the likelihood, if you like, is just 1. Right? So that means that this truth table is reconstructed directly by probability theory. That's the boring part. The interesting part is that we can also deal with, or we can also use such implied observations, even in such cases, to compute an increasing posterior probability for the hypothesis. So this forward probability is easy. The interesting bit happens with the inverse probability, with the hypothesis given the observation. So let's write down the probability for the, that's already wrong. This should be the hypothesis given the observation. That's already the first typo in these slides. Let me see if I can directly fix this. Like this. That gives you some time to read. Here I've just written down Bayes' theorem again. That's just prior times likelihood divided by evidence, and this is the sort of the expanded version of the evidence. Let's say we have a name for observing n ravens, 1, 2, 3, 4, 5, and so on. Now, if the hypothesis is true, so if all ravens are black, then the probability to observe all ravens to be black is just 1, right? Trivially. Now, if it's possible to also make other observations, if we live in a world in which we have the abilities to potentially observe white or gray or whatever ravens, so that means the probability of the converse of O is non-zero, then if we assume independence, and this word independence is this nasty bit that I'm jumping over, I'll tell you more about that in a few moments, then the probability for the observation given that the hypothesis might be false will be something less than 1. It might actually be 0, right? So epsilon could be 1. But that's the boring case, right? The interesting case is where it's something close to 1, 1 minus epsilon. And if you observe n of these independently, then we can just raise this to the nth power. Right? It's the repeated Bernoulli experiments. If you've done statistics, you've heard about Bernoulli experiments. And then that means that the posterior, and here it is wrong again, for the hypothesis given the observation, if we observe n times a black raven, will increase. Let me just fix the other bug. And it'll actually increase quite rapidly. So over here, I've plotted the posterior distribution as a function, the posterior probability for the hypothesis as a function of the number of observations. So as we go through life, we keep getting more and more confident that ravens are actually all black. And this is obviously a very, very useful ability to have in a world where we will only ever get finite data and never become perfectly confident. And in fact, classic Aristotelian logic is really just a philosophical idea that we can never apply in reality. But probability theory we can apply. Let's do another example of this. To make it even more explicit and advance warning, I'm going to ask you some questions. So here, I've shown you an example where we just infer the truth value of one hypothesis. Let's do something a little bit more complex, a univariate quantity that can take more than 2 binary values, namely a probability, a number between 0 and 1. So let's say I would like to find out which fraction of the students in Tübingen are wearing glasses. That's an innocuous question, right? Simple enough. I have an IID sample of the students of Tübingen sitting in front of me. So I could go through you somehow, through the rows, and try to infer what the probability is to, for an independent sample from the population to wear glasses. Some of you are already in the back of your head going, oh, what was independent? Oh, yeah, that's because you've had a stats class, and maybe you're just coming from a statistical machine learning lecture. That's for the statistical machine learning lecture. Let's ignore this problem for the moment and think about how we would do this in a probabilistic fashion. So, my first question is, what kind of mechanism are we going to use to infer the proportion of people wearing glasses? Whenever I ask this question, you can save yourself a lot of time or gain some reputation, positive one, by blurting out the obvious answer. Bayes' theorem. I will keep asking this pretty much every lecture from now on, and you can just always answer Bayes' theorem. Because, as I said, the entire lecture, the entire course for the next term will be about Bayes' theorem, right? So how do we do inference? Bayes' theorem. Very good. So here is Bayes' theorem. X will be this unknown quantity. X is a number between 0 and 1, inclusive, right? So it can take many possible values. For the moment, let's assume it can take only discrete values, discrete many. We decide how many we want to track, maybe 1,000. We just put a fine grid, like a lens space, right, in NumPy between 0 and 1 with 1,000 possible values between 0 and 1. Or 10,000 if you like, or how many you like. We're going to need the 3 quantities in Bayes' theorem, but we just discovered in this code piece that I showed you before that actually we only need the joint, right? One easy way to think about the joint is, so that's the numerator in this fraction, is as the prior times the likelihood. So we'll need a prior, and then we'll need a likelihood. First, what's a good prior if I want to infer a quantity between 0 and 1? 0.5 for what? Who said that? Ah, there. So 0.5 what? So you mean for every possible value the same? So for every possible value of x, I'll assign the same prior probability? Yeah, that's a good answer. What kind of probability do I have to assign then to every possible value? So uniform, right? If I assign the same value to every possible, let's say, real number between 0 and 1, then we will need to have a distribution that integrates to 1, right? So if I integrate from 0 to 1 over this thing, the answer should be 1. Otherwise, it's not a probability distribution. So that means our prior probability density at each point x will just be 1, not 1/2. Right? So we're going to use a uniform prior, and we'll set it to 1. If we do this over a discrete mesh of points, then we'll just divide by the size of each bucket, right, which is 1 over the number of buckets. So now comes the hard part. What's the likelihood? If I go through, I'm going to start actually over there. There's one person sitting who does not wear glasses in the first row on the right-hand side. What's the probability for the observation person is not wearing glasses, given that the probability for a person to wear glasses is x? Yes. 1 minus x. That's the hard part, right? So let me show you a little thing. Oh, I made a little Streamlit thing here. What you see is the prior in red. That's our prior probability distribution before we see anything. And in gray underneath, you see the two possible likelihood terms that will show up. We just had one such case. The first one, my first observation was negative, no glasses. So the probability for this observation, given that the unknown quantity is x, is 1 minus x. Another way to phrase this is to say the likelihood for x, given y equal to false, is 1 minus x. So what I will now do is Bayesian inference. I will multiply this prior, which is this red distribution that you see at the moment on the screen. I will multiply it by this triangle here, this 1 minus x function. Sorry, this one is the right one, 1 minus x. And then I will normalize. So I divide by the probability to make this observation. What's the probability to make that observation? It's the sum over all possible values of x, so the integral over x, over the prior times the likelihood. The prior was uniform, so it's just 1. The likelihood is 1 minus x. What's the integral over 1 minus x times 1 dx? You don't need to do it in your head. You can just read it off because it's an easy object. It's this triangle that divides this uniform prior in half. So it's just 1/2, right? So I divide this 1 minus x function by 1/2. I multiply by 2. Now we have our posterior. Raise your hand if you understood what just happened. That's my test to see how boring this is. That's almost no one. That means you have a question. What's the question? Is the question, I don't understand at all what's going on. Yeah, please, here in the Okay, I'll get to that in a second. What was your question?
I don't completely understand
how the figure works. Okay, I'll go back. So, first of all, let's start again with 0 observations. I've just plotted the prior. So the prior is literally, actually, do I have code for this? Yeah. Well, actually, I don't think the code will help you that much. So I will stay on this. So let me write something with a piece of chalk. Classic thing, right? So we've decided that our p of x is just 1 for all values of x in 0 to 1. That's if we think about a continuous variable. I think you're going to be fine with continuous variables for now. Actually, we need to have a lecture on continuous probability distributions on Thursday, but I guess you already accept this. So at first, so this thing clearly integrates to 1, right? So the integral over p of x dx is just the integral over 1 dx. That's just 1 if we integrate from 0 to 1. Okay? So who's following this? Raise your hand. Perfect. Thank you. Now comes the hard part. I've observed one first observation, which is 0. And what I need is this likelihood function. The likelihood is a function of x, right? Remember this picture with the arrays. We take our joint distribution over x and y, and we divide by p of y, p of x. So what is this? Well, the probability, if the probability to observe someone wearing glasses is x, then the probability to not observe them wearing glasses is 1 minus that probability. Right? So it's 1 minus x. If I had observed that person to be wearing glasses, it would be x. So the key insight here maybe that was confusing you is that you're thinking of the likelihood simultaneously as a function of x. But also you have to keep in mind that it has to be a probability distribution over y. This clearly, for every possible value of x, is a distribution over y, right? Because it sums to 1. There are just two possible values, 0 and 1. But of course, it's not a distribution in x. It doesn't integrate to 1. It doesn't have to, because it's a likelihood. So what I'm now doing, once I observe this first person who is not wearing glasses, is I am multiplying this prior with the likelihood. The likelihood is this gray thin line. Can you see the thin gray line? There are two of them. One of them is the likelihood for the positive observation. It's a function x. And the other one is the likelihood to observe the converse, 1 minus x. Right? Who can see the gray lines? Everyone? Great. And now what I've done is I've multiplied the prior, the black line, with the likelihood, that's this thin gray line. And now Bayes' theorem tells me that I need to normalize. So I need to compute. And for this, I actually do have a slide. Well, so in this first case, I need to multiply 1 minus x times 1 for the prior, and then divide by the probability for the observation y. So this is the integral over 1 minus x times 1 dx. I know maybe in your head you're going, okay, integral over 1 is 1, integral over x, 1 squared. No, you don't have to do that. You can just read it off, right? So the amount of, like the area under this gray curve, this one, is clearly 1/2, because it's half of this rectangle that has volume 1, right? Okay. Who is now following? Perfect. Thank you very much. We'll continue. Next observation, also not wearing glasses. The story continues. We just now we have a new posterior or prior. The red line is now our prior, if you like. I make a second observation. It's also negative. So I'll just increase it. I'll just multiply with this gray thing again. Now it looks like this. Who is still following? Almost everyone. So the main thing to notice is I've now multiplied in two of these factors squared, right? So now I need to, in the bottom, also integrate over this. And you can see that this is not a straight line anymore. Everything is getting a little bit more complicated. But, you know, we have computers. It's fine. Third observation, also not wearing glasses. 3 people not wearing glasses, OK? Who is still following? Yes, we haven't lost so many people yet. OK, I'll go over there. Continue in this row. This person is not wearing glasses. Next person, also not wearing glasses. Next person, ooh, now it gets interesting. Thank you very much for sitting there. She's wearing glasses. Ha! Now what do we do? So up here, I now have the number of negative observations, right? What do I do now? With the first case of observing someone who is wearing glasses. Yes? Yes, so I multiply in a new term, which is this likelihood. And I multiply it with the number of positive observations. Let's call them n plus n negative. And in here, I need to do an n plus n negative. If this is too small, don't worry, it's going to be on the slides in a second. So here comes the cool bit. I multiply by 1 positive observation. Ooh, now something has happened. All right. So now I've multiplied all these leftwards facing triangles with 1 rightward facing triangle. Ooh, there's 1 more positive observation, 1 more person with glasses. You're not wearing glasses. Let's continue here. No, no, yes, yes, yes. So no, no, yes, yes, yes. Yes, you're wearing glasses, right? And I could continue like this. Does this make sense? Have you ever seen this example before? A little bit, yeah. So this is a fundamental way to do inference that you may have encountered before. Let me go back to my slides. And it is actually an example of the very first time probability theory was probably properly used. Here is the math again. So our probability to observe for this unknown variable x, which happens to be a probability itself, but it doesn't matter. It's just a number between 0 and 1. Our posterior for this unknown quantity between 0 and 1, given that I have made n positive and m negative observations, is x to the n times 1 minus x to the m times the prior, whatever it may be. I've made my life easy and set it to 1, divided by the integral over this quantity dx. This integral over this integral here is actually a famous one. We'll talk more about it in upcoming lectures. It happens to be called the beta function. The reason it's called the beta function is that it was the second integral showing up in the paper that I haven't told you about yet. It's a very old paper. And so after alpha comes beta. Right? Yeah, so these days we can actually compute beta functions thanks to some cool libraries. But actually for today, let's keep our life simple and say, well, maybe we can get away without actually computing this beta function by just discretizing the world. So what I'll say is, as I said before, we'll just discretize x into 1,000 possible values between 0 and 1, because I'm going to make way less than 1,000 observations in here, right? So that should be enough. It's a little bit like, engineering thinking. And now my posterior distribution over x will be the prior. The prior is, well, actually it's not 1. It's 1 over the length of x, right? So each bucket in x has probability width of the bucket, which is width of the entire thing, which is 1, divided by the number of buckets, right? So 1 over len x. But it's going to cancel out in the evidence, so I don't care. The posterior is just the prior times the likelihood terms. So the likelihood terms that you saw on the screen are n times x, m times 1 minus x, and then we just normalize. So these days, this is quite easy to do by just summing. And this is easy because I have this cool machine sitting in front of me, this universal Turing machine that can do these cool computations for me, even if it's 1,000 different entries. And it does them so fast that you didn't even notice when I updated the plot. But the person who came up with this didn't have a Turing machine yet, and he is the inventor, actually, of Bayesian probability. Thomas Bayes did not invent Bayes' theorem. Thomas Bayes invented likelihoods, or maybe the likelihood principle. The person who actually invented probability theory, maybe, is Pierre Simon, the Marquis de Laplace, famous French mathematician. There's a question.
Can we go fast? I got a question about it. So in the equation, we assume that px is equal to 1, and why do we assume that px is equal to 1?
So why do we assume that px is equal to 1? Well, I just simplified my life. I just say I'm going to use a uniform prior because insert some philosophical statement about how I don't know what the probability to wear glasses is, and it seems like a good thing to do, to say everything is equally possible. But actually, in this, I will tell you, by the way, where to get this code from in a second, so you can run it yourself. I could change things here and actually change the prior. So here, what I have up here is sort of a cool trick that we will get back to in about a few weeks, which is that I could decide that my prior distribution itself is of this type. So I could say my prior over x is also of this form x to alpha times 1 minus x to beta. Now, if I set alpha and beta to 1, then that's a special case that gives me the uniform distribution, right? Because x to the 1 times 1 minus x to the 1 is just 1, and everything is fine. Sorry, if I set it to 0, so like this. right? But I could choose different values of alpha and beta, move them around to create other types of priors, to concentrate mass somewhere, because maybe I know a priori that the answer is not going to be 0 and not 1, or maybe I actually believe it's going to be 0 or 1, something like this. So Laplace actually came up with this idea, this particular idea himself as well. In the 18th century, what is this thing up there? No, I don't want that. How do I get rid of it? There's the little thing. And he actually pretty much wrote down this equation. Unfortunately, it was 17-something, no, 18-something, 1814. Well, that's at least when it was published. He probably did it a little bit earlier. And it was a bit hard to write down. So back then, people didn't actually use this sort of formal notation that we are used to now. Instead, he wrote some very lengthy thing like this. So you can read this yourself. I used to make jokes about translating this with a computer, but in 2025, nobody's surprised anymore that you can take text and translate it into English. So here we go. Back then, he wrote things down like this. And actually, Laplace encountered this exact problem. He came across this integral, this thing here, and he didn't know how to solve it. He didn't have NumPy or JAX. He didn't have a computer. He didn't even know that this integral had a name. It was too early. This integral was only invented a little bit later by Leonhard Euler. So Laplace had to make do with some simplifications, and because he was a smart mathematician, he came up with a cool approximation that we will get back to in a few lectures. And he was the first person to talk about probabilities and also the first person to encounter the central problem of probability theory, namely that because it is a statement about array-valued objects, it requires us to talk about an entire set of possible answers, about entire functions in one go. It requires us continuously to operate on like big sums like this, or actually integrals. And therefore, it can be quite hard to do in practice. And that's why statistics emerged when people tried to circumvent the challenges of probability theory. And also, that's also where problems come in, because when people ignore these integrals back there, they get statements that can be more dangerous. So Laplace came up with the first approximate answer to this problem that we'll discuss a little bit later in the lecture, and it'll actually turn out to be an extremely powerful notion that we can even still use in deep networks today in 2025 and apply them to like the largest neural networks you can think of. So the last thing I want to show you in terms of content today is that maybe a little bit of a story that Laplace, of course, he came up with this theory. He provided Bayes' theorem. He also provided this first mechanism that we just used to infer the probability to wear glasses. He actually came up with it in an attempt to answer an ancient Greek philosophical question posed by Aristotle. How do you know that the sun will rise again tomorrow? It's exactly of this type of question that I started off with before, right? How do you know, given that you've seen only black ravens, that all ravens are black? How would you know? Logic doesn't allow you to make this conclusion. Given that every morning you wake up, the sun is rising, how do you know that it'll rise again tomorrow? How would you know? There is no way in classic logic to prove this. But everyone seemed to agree that that's what we do, right? We just become confident that the sun will rise. Well, Laplace said, well, actually, here's the mechanism for this. If I just never observe a failure, then my posterior will keep concentrating further and further and further to the right, and I will get ever more confident that the sun will rise again tomorrow. So if you only have observations of this type, you can imagine that the posterior simplifies quite a bit. Everything becomes a simple polynomial. And then you can make a simpler statement known as Laplace's rule of succession, which is still used to this day to increase confidence in these hypotheses for which we assume that the correct answer will be 0 or 1. But in 1814, when Laplace came up with this, math wasn't yet formalized. He was maybe one of the first formal mathematicians, actually, to begin this kind of work. So the actual mechanism of probability theory that we use today, that is a little bit more close to you know, JAX and NumPy in 2025, was about halfway in history between Laplace and us by a Russian mathematician called Andrei Nikolaevich Kolmogorov. Any Russians in the room or Ukrainians? I hope I've roughly pronounced it correctly. Good. The first O is actually an A, and the second one as well, I guess, for us, like people in Central and Western Europe. And he published his theory of probability actually in German first, in the Springer Verlag, and under the name Grundbegriffe der Wahrscheinlichkeitsrechnung. I wanted to bring the book, but I left it in my office. I recommend that you have a look yourself. It's a neat little thin book, looks like a magazine in yellow. It's hard to get these days because he was unlucky. He published it in 1933, and Springer has a policy not to advertise books that they published between 1933 and 1945, even if they are by Russian mathematicians. But you can find them. And here is his first page. He writes down all of probability theory in basically one definition. That's this page. We'll first read it in German, and then we'll translate it into our modern mathematical way of thinking about things. So he writes, okay, I'm going to just read it in German, and if you can't read German, don't worry, it's going to be in English in a second. We'll set down our axioms of probability theory. And I guess that you've heard these before, but maybe they sort of slipped your mind. And if you haven't, now is your time to invest 10 minutes of your life in once and for all figuring out how probability theory works. And then you will never have to worry about it again. This is all of Aristotelian logic and so much more on one slide. It's the generalization of logic to the modern world. Let I, sei E, eine Menge von Elementen, welche man elementare Ereignisse nennt, und F eine Menge von Teilmengen aus E, die Elemente der Menge F, Teilmengen aus E, die Elemente der Menge F werden weiter zufällige Ereignisse genannt. And now there are the axioms, 5 of them. The first one is, F ist ein Mengenkörper. Okay, we'll have to think about that in a second. Second, F enthält die Menge E. Drittens, jeder Menge A aus F ist eine nicht negative reelle Zahl P von A zugeordnet. Diese Zahl P von A nennt man Wahrscheinlichkeit des Ereignisses A. Okay. Fourth axiom, P von E ist 1. And fifth axiom, wenn A und B disjunkt sind, so gilt P von A plus B ist P von A plus P von B. Ein Mengensystem F mit einer bestimmten Zuordnung der Zahlen P von A, welchen diesen Axiomen genügt, nennt man Wahrscheinlichkeitsfeld. That's it. That's a very typical kind of mathy definition. And your question now is, what? Right? So this is always what happens when you see a math definition. Who in the room studies math, like as their main degree? 1, 2, 3, 4. So you're used to this. It happens in every single math lecture, right? In the first lecture, on any course, you come in, someone writes down axioms like this, and by now you got used to it, and you've also had your undergraduate math lectures, right? You know this. You had your theory of computer science that's full of these definitions. And now what you do in your head is what you always do when this happens in lectures. You concentrate very much, and then you read this again and try to figure out what's going on and why it's so important, okay? Let's do this together. So first of all, what is this Mengenkörper? Well, actually, Kolmogorov has it in a footnote, and he says, I got this idea from Hausdorff. Here it is. So, Mengenlehre. Ein Mengensystem heißt Mengenkörper, wenn die Summe durchschnittliche Differenz von zwei Mengen des Systems wieder dem System angehören. Jede nicht leere Mengenkörper enthält die Nullmenge und wir bezeichnen. What he's actually saying here is the following. I had this picture on a previous slide, right? So here's another picture like this. What he's saying is, I want to be able to draw this picture. That's it. That's the entire statement. The whole point of this is, I want to think about situations where I'm allowed to draw this picture. So what do I need to be allowed to draw this picture? Well, I need a space, E, so I need to be able to draw the rectangle, okay? Then this space E needs to contain sets. Well, sets are made up of elements, so I first need to assume that there's something called elements, right? So for him, that's the space E, and it contains these elements, which he calls atomic elements, or elementare Elemente, elementare Ereignisse. And now, is that out of these elements of the space E, I want to be able to build sets, A and B, and then I want to make sure that no matter how I build these sets, I can always also talk about their intersection, their complement, their union, and their differences, so the quotient sets. So I want to be allowed to do this. And that's it. That's the first axiom. So today, in 2025, or actually since the 50s, we would write this like this. We would say there's a first definition, which we call the definition of a measurable set. And it contains this scary object called a sigma algebra. Who has heard of a sigma algebra before? Yes, everyone. Did you still remember what it was? If I would have asked you what's a sigma algebra, who would have, raise your hand if you could have defined it? Yeah. So why? I think this is because of this name. It's because someone decided to give it this big, scary name, sigma algebra. Sigma algebra just means I want to be able to draw this picture with the intersected circles. I want to be able to draw Venn diagrams. That's it. So let E be a space of elementary events. Consider the power set of these events, and let F be a subset of this power set. So a collection of sets. Right? So E consists of elements, and we are interested in sets that contain these elements. That's it. We will call these events, these elements of F, we will call them elementary events, and we will call elements of this power set random events. Here's the first time the word random. Random comes with a lot of philosophical baggage. I will argue that randomness doesn't even exist later on. It's just a word. It just means random events. It's just a name for sets. Now, we call such a space a sigma algebra, or actually we call a collection of such sets sigma algebra if it has the property that it contains the entire space, so we can talk about the whole space, that whenever I have a random event, so one such set, the complement is also in the sigma algebra, and if I have a bunch of sets, then their union, and any countable such union, will also be in this thing called the sigma algebra. Now, if I have these three properties, I actually automatically get also closure under intersection and differences, because they are constructed, they can be constructed from union and complementation. And you will remember this if you've ever taken a set theory class or your theory of computer science, you may remember this, De Morgan's laws, and then you might convince yourself that you can do this. And actually, Kolmogorov has the same thing on his, in his definition that I just showed. Here we go. This is like this is then automatically in there, basically. Okay, so such spaces are called measurable. They are just my ability to draw Venn diagrams. Done. And now he says, here comes the new thing. I don't just want to be able to draw these Venn diagrams. I also want to be able to talk about the volume of these assigned to these circles, to these sets and their complements. And to be able to do that, I need to assign a volume to the entire space E. I will call this the measure of E. That's where the word measure comes from. And then I just need to make sure that my way of assigning measure to a set is sort of commensurate with these operations that I want to do on the sets. So in particular, if I have two disjoint sets and I've assigned measure to both of them, then the measure of their union should be the sum of those two measures. Right? And that's exactly what the second set of axioms says. This is called the definition of a measure, not a measurable space, but a measure itself. Let's say I have such a measurable space. A measurable space, remember, is the set E with its sigma algebra on it, with this collection of sets. This is also called a Borel space, by the way. Then a non-negative function, so a way to assign volume, and we will assume that volumes are non-negative, is called a measure if it has the property that the empty set has measure 0, and for any countable sequence of pairwise disjoint sets, the volume of the union of such disjoint sets is the sum of their volumes. And that has the fancy name sigma additivity, yet one more word to scare you away. But it really just means I need to be able to deal with these Venn diagrams. And now the trivial extra thing to be able to talk about probabilities is to say, I'm just going to say the whole volume, E, will have a specific amount of measure. I could pick any number, but it seems convenient to set it to 1, right? Because what else? If I would decide to set it to 3, that would just complicate things. So I'll set it to 1. That's it. Those are our definitions, and now we're done. The rest, with two little exceptions, is the usual thing that happens at the beginning of lectures like this. We now have our axioms, so now we can go through and apply them and see what we can do with them. You've played this game before in undergraduate math lectures. Professor writes down a bunch of axioms, and now we spend the next 20 minutes just applying the axioms and seeing what we can get. The first thing you can get is called the sum rule. So we notice that any set plus its complement is equal to the whole set E. So therefore, the probability assigned to, so by axiom 4, the probability assigned to E is 1, and therefore the probability assigned to A plus the probability of the complement of A is 1, because A and its complement are disjoint. So therefore, we have this rule of complementarity, sort of, right? So the probability for A is 1 minus the probability for its complement. And I've already used this in some of the examples that I started with. We can rewrite this and say if we use the notation of joint probabilities, which we will write like this, so the probability for A intersected with B, we will write as the joint of P of A and B. Then we realize that because we can do this for B, right? So B plus not B is E. We can basically write A as the intersection of A with E, and E can be written as B plus not B. So therefore, the probability of A is the probability of A and B plus the probability of A and not B. And this is actually an interesting logical rule. It allows us to introduce a new variable into our reasoning by considering the two possible values that it could have if it's a Boolean variable. Or in the complement, to read the equation from the right to the left, it allows us to get rid of a variable we don't care about or a variable that we don't know by summing over it. And we've used this in the examples. Now Kolmogorov introduces a new quantity which he actually has to define, called a conditional probability. You've already seen conditional probabilities, so I'll make life easy for us and say we define the conditional probability as P of A and B divided by P of A. We've talked about this before. Why does he do it this way? Is it bad that he has to define it? Is there no natural way to construct it? Actually, there is a natural way to construct this, and it is the only natural way to construct it, because his goal is to define a notion of a conditional probability that itself adheres to the definition of a probability. So you can convince yourself, and that's down here, you can read this later, that this conditional probability distribution actually is itself a probability distribution. And one can show that this is pretty much the only natural way to define such conditional distributions. There is a famous text by an American logician called Richard Cox, who basically had a whole philosophical treatise about how this is the only way to define it. But Kolmogorov doesn't spend much time on it. He just does it in 3 lines and says, that's the definition. Because if we define the conditional distribution like this, then we can use the results from before with A and not B, right, the sum rule, to generalize the sum rule to this statement, which we sometimes call the sum rule, or the general sum rule, or the law of total probability, which we use all the time, right? To get rid of an unknown variable A, we just sum over all possible values that it could take. This is the first real problem of probability theory, because hidden in there is a nasty philosophical assumption that you know all possible things that could happen. So when we make our statements about how, having only seen black ravens, I become ever more convinced that all ravens are black, or having only seen the sun rise every day, I become increasingly convinced that the sun will rise every day, this is one of the assumptions we make under the hood, that we just know all the possible things that could happen. Once I learn about supernovae, maybe my posterior changes somehow, but so far I haven't considered this in my space of hypotheses. Or about, you know, magpies, right? Ravens that aren't just black. Now, and now as a final sort of statement, well, once you have this, you can obviously just rearrange these expressions and get this thing called Bayes' theorem. So the important thing, I mean, we don't have to do the proof here, right? You've done this many, many times before in your life. The main thing to take away here is Bayes' theorem is completely unproblematic. If you've ever heard someone criticize Bayes' theorem, they've just criticized set theory. You're really worried about set theory on finite sets? Nah, right? So Bayes' theorem is completely uncontroversial. The controversial bit, first of all, is this law of total probability, the assumption that you know all the possible things that could happen. And secondly, this thing, because there's a final definition that I have to mention to you that you've also seen before, and it's the definition of independence. So if we have two random variables A and B, and their joint distribution can be written as a product P of A times P of B, then we call them independent. Who has heard this definition before? I hope everyone raises their hand. Thank you very much. Good. See how easy this all is? So in terms of arrays, that means if we can write this matrix, this array that makes up P of A and B, as an outer product of two vectors, P of A times P of B, then we call them independent. And there's a corresponding statement for conditional independence. Raise your hand if you've seen this before, and I don't have to define it again. Yeah, it just took a second for everyone to get to it. Yes, okay. So conditional independence. So it's clear, obviously, that such distributions exist, right? Because there are matrices that can be written as rank 1 outer products. Clearly, these things exist. So maybe it's good to have a definition for them. They are called independent variables. So the fact that they exist is not the problem. Whether we are allowed to call two random variables independent is a huge problem. And it is actually maybe the fundamental problem of this entire notion of inductive inference. So of extracting information from data, from observations. And it will be all over this course in the next, 12 weeks, including in your very first homework exercise. And we will get a lot of time to talk about it in various different ways, mathematically, in code, philosophically, and it'll just be all over the place. However, this is not a specific problem of Bayesian inference. It's a problem of probabilities. And therefore, it's inherited by statistics as well. So if you're going to the StatML class, the word IID will show up a lot, and it'll inherit all of these problems, actually. So if you've ever heard that there is some sort of century-old debate between the Bayesians and the frequentists, between the probabilists and the asymptotic people, the statisticians, the statistical theorists, then you may have heard that people argue over the notion of a prior, or over a likelihood, or over the application of Bayes' theorem. That's wrong. Bayes' theorem is not controversial. The idea of a prior measure is not controversial because it's just set theory. The two problems that we have in this kind of philosophy is this notion of total probability, so the assumption that you know the whole space of possible events, that you know all the things that could possibly happen, and the idea of independence, the idea that you can think about one thing without having to consider another one. That's what I wanted to tell you today in terms of content. It's a bit dry, I realize, and it's always a bit problematic that I have to start a lecture with this dry stuff. Thankfully, on Thursday, we'll do a little bit even more dry stuff, actually. Maybe it'll drive away some of you. I hope it doesn't. I hope you stay and sort of survive this first week. And then after that, we'll do lots and lots of cool code, okay? And actual machine learning. So this is the bit where we switch to the administrative mode, because every every term has to start with a little bit of background on what this course is going to be. Let me first tell you a bit about what to expect from this course. What I'm trying to do with this probabilistic machine learning class that I've been actually taught for a long time already in always changing formats, every time I teach it, roughly every other year, about a third of the content is completely new. This time, I'm going to try and make it all about broadly applicable patterns, rules and recipes for thought and code that you can universally or generally apply to extracting information from data or other kinds of statements. That other kinds of statements will be quite prominent in this year's instance of probabilistic machine learning because not every instance of learning, especially in 2025, involves floating point numbers provided to you on a disk in the form of images or texts or integers maybe, right? It may also include things like symmetries, differential equations, laws of nature, conserved quantities, and other forms of knowledge. I should tell you that probabilistic machine learning as a lecture course is deliberately next to statistical machine learning. It's deliberately on the same day of the week so that you can walk over from one of the lectures to the other. When we designed the probabilistic machine learning master, sorry, not probabilistic, that's a Freudian slip, the machine learning master, which, by the way, mostly to blame for this are Matthias Hein, Ulrike von Luxburg, and myself. When we wrote down the curriculum for this, we wanted to have a core part in the second term, in the summer, where you get exposed to the rigorous fundamental ideas of machine learning in a way that generalizes and hopefully lasts for longer than the current cycle. There are other places in the world that deliberately only focus on the most recent ideas. If you go to Stanford, you get told that you are only going to learn about things that are half a year old at most. If you come here, we'll try and give you ideas that will hopefully last for at least a decade, maybe a century from now. And to do that, we have to try and tease out some fundamental ideas. And in the statistical and probabilistic machine learning class, we're trying to do just that. And now we deliberately put them next to each other so that you get exposed to two different ways of thinking about these ideas. In this year, once by Matthias Hein and once by me. And then in other years, it's Ulrike von Luxburg and Jakob Macke who are teaching these classes. And we put them next to each other so that you can really sort of experience this whiplash of two different ways of thinking about this field by coming to both of them. However, that doesn't mean that these two classes will be super synchronized with each other. I mean, you probably already noticed in this first lecture now. In fact, I don't even have Matthias Hein's slides. I have his curriculum, I know what he's covering, and we had a long meeting to discuss that, but I'm not going to point out specifically, oh, this is like slide 45 on Matthias Hein's slides, right? Because that would be pretty much impossible for us to coordinate. And that also means if you're not in the machine learning master or you feel that this is way too much and you only want to take one of the classes, it's totally fine to just come to this class. Right? But if you want to get like the full explosion in your head, then come to both. The reason, so I also realized that Tübingen has a bit of a reputation worldwide for being a place where there's quite a theoretical education and it's maybe not so practical. I don't know whether that's true actually. I think a lot of the stuff we will do is quite practical. But we do value a lot the mathematical foundations of machine learning. And that is because it's not like accidental. It's not just because we like to be theorists. It's because historically this has been the one thing that has made machine learning successful. There are other communities, I'm not going to name any of them because it would be unfair, right? That came and waned because they either put too much focus on theory, they tried to be all pure math and then nothing ever came out of them, or they were just too empirical. They just came up with, oh, like I spent an afternoon looking at an anthill and now I have an idea for a new algorithm that works a little bit like an anthill. And then let's just see if that works and never do any theory for it. I've been in, like, I'm now increasingly feeling a bit like an old man, especially in a room like with young people like you. And I've been in this field for a bit, right? not like for the whole time, but I think I've seen more than half of the history of machine learning in person. And this has always been a hallmark of this community, that there is, just like in physics, there's some kind of interplay between the empirical and the theoretical parts. And sometimes the empirical part takes over because our community allows people to do crazy stuff, to just try out something and see if it sticks. Everything goes, is what Moritz Hart says. And then the theory part of the community catches up. It starts asking questions. It says, what, really? But this should not work. Now let's do this other experiment. See, it doesn't work if you do things this way. Let's fix this. Let's do it correct. Or actually, you can think about all of these 5 different things as instances of the same idea. So now I can take it and generalize it to something much broader. That's what happened several times in the past, and it has really moved the field forwards. Just like theoretical physics has at times pushed forward empirical physics, experimental physics, and then at other times, new experimental results sort of push the theorists to do new things. So therefore, we will here do a lot of math, but also a lot of code, and I will try and switch back and forth all the time. We will also have to do approximations quite frequently. So those of you who come from a math background, you will often feel that you're in a sort of a dirty environment where we just do something a little bit, we'll just do it so that things work. Just like I did today with this Lin space, right? Not actually an integral. Let's just get rid of it very quickly. I'm also very much trying, and I tell you this because I hope that you will appreciate it. I am very much trying to stay close to where the field is currently. And that means that a lot of the content we will do this year is new. It will also sometimes mean that it's a little bit shaky. So occasionally you will see code from me that is completely without comments because I had no time to write in the comments. I just made it work. Sometimes you will see code that is maybe not exactly beautiful Python because I didn't have time. I just wrote something down. You'll see Jupyter notebooks where we just import stuff and then like overwrite it and do some stuff that isn't quite beautiful. I invite you to enjoy this slightly wild ride. Okay? And when that happens, it's because I'm trying to stay close to where the field is moving. So what are we going to do? What's the content you can expect? Well, here's a few things you can expect. Just a few ideas. Just a week from now, we will start talking about Gaussian inference, and we will encounter that all of numerical linear algebra, all these fundamental algorithms that you have encountered in your numerics classes in your 3rd term or 4th term of your computer science or math degree, turn out to be inference algorithms that can be stopped at any point in time, and they return a posterior uncertainty over the solution of linear problems. That's one example of the universality of Bayes' theorem. It's the practical instance of this case, this claim that I've just made, that probability theory is a genuine generalization of propositional logic. And this will come with code. Then we will talk about Gaussian processes and kernel machines, and we will realize that they relate to parameterized versions of machine learning analogously to how functional programming relates to object-oriented programming, how lazy evaluations relate and higher order functions relate to imperatively defined objects. We will also discover that this framework can be used to learn from quite general notions of information, from knowledge that is not explicitly instantiated as bits on your hard drive, but that can be realized and instantiated at compute time in arbitrary resolutions if necessary, for example, to solve differential equations or to include knowledge about conserved quantities and symmetries in a system. And this is, of course, quite important for scientific applications of machine learning, where the knowledge we have about the world often does not come in the form of data, but it has already been abstracted to laws of nature that we then have to somehow get into our learning machines. And as we increasingly talk about machine learning being applied in material science, in climate science, in biology, and so on, we need to have this kind of functionality. It's maybe not so relevant for language and images, the two traditional applications of machine learning, but for these new applications, this is much more important. We will then talk about quite an interesting thing that we call an exponential family, which turns out to be an abstract base class of a learning machine. And we will discover that we can use inheritance there, that you all know as computer scientists, to create a general notion of what a learning algorithm is that actually relates directly to the idea of a loss function. So if you've ever wondered where loss functions come from in deep learning, you will figure out exactly what the space of possible loss functions is. We will then also talk about, quite generally, all differentiable programs, so deep neural networks, if you like, but actually maybe something more general, differentiable programs, and discover that when we relate them to these loss functions through data, we can think of them as approximately probabilistic models. And we will be able to turn any deep neural network into a probabilistic model, in fact, into a Gaussian process, for those of you who are following from probability theory, using language from differential geometry. So if you like differential geometry, if you like relativity theory, then stick around for this time, and you'll learn a pretty beautiful framework that is computationally tractable and turns every deep neural network, every single one you can think of, into a probabilistic model. Towards the end, I will maybe do, if there is time, some philosophical spiel about how randomness doesn't exist. And you will notice over the next few lectures that I will keep pointing out every now and then that we're not going to be using random numbers. If you came here thinking that probability has something to do with randomness, you are wrong. And we will talk about this. Randomness does not exist. And then finally, I wondered how in 2025 I can talk about transformers and attention and where they come from. And as of now, it looks like that will turn into a bit of a history lesson. And we'll find out, we'll try to trace back through time, 100 years into the past, where attention actually comes from. So that's what we're going to do. I hope that motivates you to stick around. So if there are no more questions, before you all run away, it's 37, I want to leave you with this thought on independence. I've realized that it's maybe a bit corny to say independence is a questionable concept, but it is actually very important. If you want to understand the problem people mentally have with statistics, with inference, with probability theory, independence really is the thing that should worry you. And here is in the original words of basically the inventor of modern probability theory. In paragraph 5, he says, der Begriff der gegenseitigen Unabhängigkeit, the notion of mutual independence between two or multiple experiments, is actually the central concept of probability theory. And indeed, we have seen that probability theory from a mathematical perspective is basically just set theory. That's what he says here, right? So we could wonder whether, if it's just set theory, probability theory really should even be considered a field of its own. Is it even a new thing? It's clearly consistent because we know that set theory is consistent, right? Except for the usual problems with the axiom of choice that we'll discuss on Thursday. So historically, is actually the independence of experiments, this notion of being able to write measures as outer products, that gives probability theory its specifics, its eigenartiges Gepräge. And the classic works of Laplace, Poisson, Chebyshev, Markov, Ljapunov, von Mies, and Bernstein are indeed basically works on independence. And we will discuss this the entire time. So we then come to the conclusion that the notion of independence is the core of the problems of probability theory. And Kolmogorov says, I don't care. In my book, I'm just going to assume, because I'm a mathematician. The philosophy I'll leave to other people. Okay, I'm doing him a disservice because he actually spent a lot of time thinking about it. He also originally translated the works of Markov from the Russian to German and English to get people to think about them, because he was very concerned about them. He also provided this notion of randomness that we'll discuss later that is super helpful in this. So philosophers of science should really worry about independence. And if you want to have something to discuss over lunch, then please think about independence. This is the summary for today. Here's the QR code. Please scan it and give some feedback about today's lecture. What have I told you? I've told you that probability theory is a formal generalization of the classic notion of logic. That's why it is so important today. And Machine learning is just the mechanization of this inference process. AI is just a mechanization of this inductive reasoning realized on Turing machines and actually on massively parallel Turing machines in 2025. So if we can translate these mathematical ideas onto computers, then we can formalize this inductive reasoning. Bayes' theorem itself is not controversial. The law of total probability and the notion of independence are controversial. And what we're going to do over the course of this term is to take this notion and see how much we can do with it on a Turing machine and also on massively parallel coprocessors on Turing machines. How does this all differ from statistical machine learning? Well, if you really want to know, you have to attend both and just find out. Thank you very much. See you on Thursday.